Thermodynamics in Biosystem Module 1, Segment 2, Thermodynamics and Energy, with me, Yusuf from Institut Teknologi Bandung. Thermodynamics can be defined as the science of energy. Energy can be viewed as the ability to cause changes. The name thermodynamics stems from the Greek word therm, which means heat, and dynamis, which means power, the most descriptive of the early efforts to convert heat into power. Today, the same name is broadly interpreted to include all aspects of energy and energy transformations, including power generation, refrigeration, and relationships amongst the properties of matter. One of the most fundamental laws of nature is the conservation of energy principle. It simply states that during an interaction, energy can change from one form to another, but the total amount of energy remains constant. That is, energy cannot be created or destroyed. For example, Figure 1 shows that a rock falling off a cliff picks up speed as a result of its potential energy being converted to kinetic energy. Figure 1.2 shows conservation of energy principle for human body. A person who has a greater energy input than energy output will gain weight, and a person who has a smaller energy input than output will lose weight. The change in the energy content of a body or any other system is equal to the difference between the energy input and energy output, as shown as by the energy balance. The first law of thermodynamics is simply an expression of the conservation of energy principle, and it asserts that energy is a thermodynamic property. The second law of thermodynamics asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. For example, Figure 1.3 shows that a cup of hot coffee left on a table eventually cools, but a cup of coffee in the same room never gets hot by itself. The high temperature energy of the coffee is degraded or transformed into a less useful form at a lower temperature once it is transferred to the surrounding air. Although the principles of thermodynamics have been in existence since the creation of the universe, thermodynamics did not emerge as a science until the construction of the first successful atmospheric steam engines in England by Thomas Savery in 1697 and Thomas Newcomen in 1712. These engines were very slow and inefficient, but they opened the way for the development of new science. The first and second law of thermodynamics emerged simultaneously in the 1850s, primarily out of the works of William Rankine, Rudolf Clausius, and Lord Kelvin. The term thermodynamics was first used in a publication by Lord Kelvin in 1849, whereas the first thermodynamics textbook was written in 1859 by William Rankine. There are two different approaches to thermodynamics. First is classical thermodynamics, which is a branch of physics concerned with the conversion of different forms of energy. As a phenomenological theory, it deals with microscopic objects and properties that can be observed and measured in experiments. However, many questions remain open. For example, why do all gases behave similarly? What is entropy? It provides no information about the states or existence of molecules. That brings us to the statistical thermodynamics, which is a branch of physics that describes the thermodynamic behavior of microscopic systems based on the properties of their molecular constituents. It gives thermodynamics a molecular interpretation and serves as a bridge between macroscopic and microscopic system properties. All activities in nature involve some interaction between energy and matter. Hence, thermodynamics is commonly encountered in many engineering systems and other aspects of life. The heart is constantly pumping blood to all parts of the human body. Various energy conversions occur in trillions of body cells. Body heat generated is constantly rejected to the environment. We try to control this heat transfer rate by adjusting our clothing to the environmental conditions. An ordinary house is typically filled with various applications of thermodynamics as shown in the figure, such as electricity, heating, air conditioning system, refrigerator, humidifier, pressure cooker, water heater, shower, iron, and even the computer and the television. On a larger scale, thermodynamics plays a major part in the design and analysis of automotive engines, power plants, artificial forests, and many others. For the next segment, we will discuss about dimensions and units. Until then, I am Yusuf from Institut Teknologi Bandung.